So we're very happy to continue with the second part of Professor Teissier talk on geometric introduction to valuation theory via infinite dimensional algebraic geometry. Professor?
Thank you very much. So we've seen that already in dimension 2, we are faced with valuations which involve infinite dimensional spaces or equivalently non-finitely generated semigroups. So it has given you an idea that dimension 2 is very different from dimension 1 already. Now, in the sequel, we're going to look at arbitrary dimensions. And it becomes, of course, much more complicated again. So one of the things on which I passed very quickly was when you I go back briefly to dimension 2, when you blow up the origin, let us say, and we take a point on the exceptional divisor, and we look at valuations centered at that point. So what does center mean? I told you evaluation begins with functions, rational functions, which have a zero or a pole or a finite value at some point. What is that point? If I take the first valuation I talked about, which is the order at the origin, I go back like this, my polynomial becomes x prime to the s, p prime of x prime and y prime. And this is the order of vanishing at the origin. But because x prime equals 0 in the chart in which I'm looking at things is the equation of the exceptional divisor, actually this s is the order of vanishing of the, let's call pi the projection map. This s is the order of vanishing of p composed with pi along the exceptional divisor. So if I look at it in this new surface, which is the blowing up, the center is no longer a point. The thing along which my polynomial vanishes is the whole divisor. And in fact, this is the correct notion of center in this case. The correct notion of center is not this point. It is this divisor. So we have to understand better what the center means. And we realize that it is not something which is invariant under blowing up. Here we have one point, here we have one divisor. But be reassured that if we continue blowing up points, my exceptional divisor will have strict transforms. Let's say this, that. And from this point on, the center will always be the strict transform of that particular divisor. So the things do not get worse and worse and worse. They stabilize, in this case, immediately. But let's go back to what is the notion of center. So we have a field of rational functions. So the field of functions on some variety. Now I'm in arbitrary dimension. In this, I always have a base field, which I tend to forget, and all the valuations I talk about are trivial on the base field. We have a valuation ring. And now, what does it mean to have a center for an algebraic variety? It means that there is, if my variety x is covered by affine varieties, it means that one of the rings here, so all these rings are subrings of K of x with the same field of fractions, and it means that this particular valuation ring contains one of those alphas. It can contain more than one. And then the center will be defined as the intersection of the maximal ideal of R nu with A alpha, which is a prime ideal. And in fact, in the theory of places, people already thought of points irreducible varieties as points. Points where a rational function vanishes. And it's something which was really in the collective mind, clearly. So so it may very well be, suppose you have a plane curve, and your valuation, it's in the plane, the affine plane, and your valuation has a center at infinity. Then there is the ring of my curve is not contained in the valuation ring. So to have a center is not something that happens all the time. In fact, the fundamental theorem is that if I have algebraic varieties like this, if every valuation of K of x has a center in X, then X is proper over K, and conversely. It means there are no points at infinity that are missing. Properness means that. I'm not going to go into the details. You can go to your favorite algebraic geometry book to look at the definitions, but properness means there are no points missing. And there is a relative version of this theorem that says that if I have a birational map, so it's birational, which means the fields of fractions are the same, then it is proper if and only if every valuation which has a center in X has a center in X prime. If you're a beginner, it's useful to think of this like that. You have a map, and to say that it is not proper basically means that in some fibers points are missing, the points at infinity, so to speak, in that fiber. Now, you can think of evaluation. This is, of course, just a kind of psychological image. You can think of evaluation as a curve going through these points. And because your map is birational, this is again waving hands in a very heavy way, you can imagine that you can lift the part of the curve which does not contain the origin. And if you have bad luck, the closure of this lift will not exist in X prime because the point is missing. So, and this, imagine that this was giving you a valuation, the other vanishing along this curve. So this valuation will not lift. So that is the essential meaning of the valuative criterion of properness. If every valuation lifts with a center, then it means the morphism has to be proper. So I erase this. Of course, now it's on video, so it's but I take my responsibilities. Okay?
After the video can be erased.
Yeah.
You can ask.
Yeah, I can ask. Then we have to negotiate. So, why do I say this? Because the notion of center is essential in understanding the nature of valuations. And this is embodied in the theorem of Zariski, which is like this. First of all, you put a topology. I'm always in the same framework, K of X, on the set of valuations. So I'm going to describe a basis of open set. A basis of open set in this topology is the set of valuation rings which contain F1 up to Fn. So the valuation rings which contain a given set of rational functions, that means the rational functions take positive value, so to speak, with respect to this valuation. This is a basic open set. So your open sets are union of these, an intersection of these basic open sets. So this describes a topology on the space of valuations. I'm always talking about valuations which are trivial on K. So on one hand, I have the space of valuations with this topology. That's why I say space. On the other hand, suppose that X is proper. I say this to simplify life. Then, if I take any birational map, because of the valuative criterion, my evaluation will have a center on each birational model. I can continue. The birational models of X constitute a projective system. That means if I have my X and two birational models, there is always a third one which dominates them both birationally. This is quite classical. And so this is proper birational because they constitute a projective system. there is a projective limit. And now I'm going to define a map following Zariski from this space to that space. I take a valuation here, and then I take the collections of a center of nu in x prime. This is well defined. It's a sequence of points of x prime, but they are points in the sense of scheme theory. They are not closed points, they are points in the sense of irreducible subvariety, because you must remember that a center is an irreducible subvariety. Okay? Like here, I have an irreducible subvariety which maps to a point. Okay? So this is a point in the sense of scheme theories, if you like. So this is a map, and the theorem of Zariski is that this is a homomorphism. If here I take the projective limit of Zariski topologies. With respect to the base field, always on x prime. With respect to the base field means the closed set are the closed set defined over k, little k. The paper where Zariski proves this is actually the paper where he first talks about Zariski topology. He introduced the Zariski topology in order to be able to prove this and to prove the theorem which was most important for him, which is that this limit, if x, again, if x is proper, is quasi-compact. It is no longer an algebraic variety. It is not even a scheme. It's a very complicated space. But it's a very fascinating object. And when one studies valuations, one has to, or even one thinks about resolution of singularities. I'll say just a few words. That Zariski's program was to say, suppose I can, for any given valuation, I can find a model on which the center of that valuation is non-singular, on that model. Then, because the property of being non-singular is an open property, there will be an open set in the space of valuations which will have a regular center on that model. So that will give me open sets in this. This is called, by the way, the Zariski-Riemann manifold. So there will be x prime, because it's quasi-compact, it will be covered by finitely many open sets, such that for each valuation in one of those open sets, there will be a model in which the center will be non-singular. Then the program of Zariski. So you see the Zariski-Riemann manifold will be covered like that. Each valuation here has a center non-singular in a certain given model, a certain x prime. And then all I have to do is to, between quotation marks, is to find a single model which will sort of dominate all those. The problem is that this domination is extremely difficult. It was solved by Zariski in dimension 2, but it's very, very difficult in general. Dimension 3. Yeah, dimension 3, using resolution in dimension 2. So the possibility of finding a model on which the center of a given valuation is non-singular is called local uniformization for that valuation. Okay. And this is the problem I wanted to talk about, anyway. And before I explain to you the approach which I would like to use, I must go back to something much less fancy than this, which is to look a little bit at the classification of valuations in general. So let me explain a little bit. So I hope it's clear that we are now in arbitrary dimension. We are looking in principle at arbitrary valuations, and we would like to understand them sufficiently well to be able to produce models, or if you like, birational maps, on which the center of the valuation becomes non-singular. Now it turns out that using the semigroup, which I introduced earlier, valuations produce combinatorial objects. And we're going to use a lot of combinatorics in order to understand what is going on with valuations. How do they produce combinatorial objects? Well, I told you that the semigroup, so first of all, if R is Noetherian, which it is in our case, contained in some valuation ring, let us say, then the semigroup of R which is a sub-semigroup of the positive part of the valuation, of the value group, is well ordered. I showed you that in the case of Z2 Lex, if you remember what happened an hour ago, it was not well ordered. But the semigroup is. Why? Because we look at the ideals for every phi in the value group, we can define an ideal in R. The idea of elements whose value is greater than. I told you what was important with valuation is that they measure the order of vanishing. So when you have a measure, you always try to find a filtration, which explains to you how the measure behaves. In the case, if I want to do this in the general case, including the case where phi may be R may be R nu, for example, so gamma is phi positive, the element phi may not have a successor. There may not be a smallest element which is greater than phi, so we define another ideal, which always makes sense by simply putting a strict inequality here. And then we produce a graded ring. And this graded ring is indexed by gamma. Why? Because if phi is not an element of gamma, it means that there is no element of R whose value is exactly phi. Therefore, if an element has value at least phi and cannot be equal to phi, it has to be greater than phi. So it has to be 0 in the quotient. So this graded ring is actually indexed by the semigroup. And because it's a semigroup, it makes sense to say that it's an algebra, of course. Now, this graded ring contains a lot of information about the valuation of the ring. And it already has some combinatorial nature because the semigroup appears here. But we can do better than that. If I do the same thing for gr nu, R nu, well, everything I said makes sense. And now all the values, all the positive values are attained, because by definition. And this, by construction, this algebra is a subalgebra of that algebra. And now here comes the miracle. So be prepared. There was a picture in the New Yorker like that. Of a guy making a talk in physics, and he says, and now a miracle happens. Well, let me tell you, it's a kind of miracle, actually. What is the miracle is that this algebra has the property that every homogeneous component here is a one-dimensional vector space over K nu. K nu is the residue field of R nu. This is very obvious, because if you take two elements which have the same value, then by definition, it means that they differ by a unit in R nu. That's the definition of a valuation ring. Now, if I look modulo elements of higher value, the unit becomes an element of K nu. The unit is an element of K nu modulo. So it means that any two elements here, one is a multiple of the other by a factor in K nu. As a vector space, it has to be of dimension 1. On the other hand, it cannot be 0, because all the values are attained by definition in the valuation ring. Now, suppose that we know that K is equal to K nu, that the residue field of R is equal to K nu. Then this subalgebra is exactly that part of this algebra where the degrees are in gamma. Is it clear? Because these are non-zero. They are subvector spaces of a one-dimensional vector space. Not much choice. Okay. So it has to be that this subalgebra consists exactly of restricting myself to the degrees that are in gamma. But then this subalgebra also has the property that each one of its homogeneous components is one-dimensional. But when you see an algebra like that, it should remind you of a case where you know that this is the case. It is the case of a semigroup algebra. If you take a semigroup and a field, and the semigroup algebra what is the dimension of the homogeneous components? One. And in fact, it is true that Grö nu R is isomorphic in a non-canonical way with, always under this assumption, of course. But these are the valuations which I want to study. If you look at Zariski's theorem, the valuations which have this property are the valuations such that in every birational model, the center of the valuation is a closed point, is a rational point, I should say. Is a rational point. But because I take usually K algebraically closed, it comes to the same. But so I call them rational valuations because they correspond to the rational points, so to speak, in the Zariski-Riemann space. But if you can uniformize when the center is a point, that means your ambient variety is non-singular at the point. It will be non-singular along any subvariety. So if you can uniformize those, you can uniformize all. What I just said is not a proof, but it's the reason why it's true. Okay, so these are really the important guys in the story of local uniformization, the rational valuation. And they have this nice property. And when you see this, it means that because gamma is well ordered, oh, I forgot to say, I started, but I forgot to tell you, why is gamma well ordered? Well, it's very simple. If I have an infinite decreasing sequence of elements of the semigroup, I have an infinite increasing sequence of ideals in the ring. But my ring is not Theorem. So the story ends there, after finitely many steps. So it is well ordered, and because it is well ordered, it has a minimal system of generators. Even if it is not finitely generated, you take the smallest non-zero element, the smallest non-zero element which is not a multiple of this one, the smallest non-zero element which is not in the semigroup generated by the previous one, and you go on like that. Except that you may have to go on transfinitely many times. Because the ordinal type of the generators of the semigroup may not be omega. It's not finite because we are not assuming that it's finitely generated, but it may even be larger than omega. But thanks to a theorem which I think is due to Krull and which is in Zariski's book, the ordinal type, so the gammas are indexed by I, and I as an ordinal is less than omega to the dimension of R. So it's not a very nasty, ordinal. So you must learn to work in spaces where you have coordinates which are indexed by an ordinal. This is what I mean by, in this case, infinite dimensional algebraic geometry. Okay? And why coordinates? Because, again, under this assumption that K is K nu, there is a bijection between those generators and generators of the K algebra Grö nu R, because the degree of the generators of this algebra have to be generators of the semigroup. That's clear. Okay, so this guy is not uniquely defined. It's uniquely defined modulo multiplication by a non-zero element of K star. And this is why this isomorphism is not at all canonical, because it depends on the choice of the generators here. But then when I have generators of an algebra, the first thing I want to do is to present it as a quotient of a polynomial ring. By taking as many variables as there are generators, this is my ordinal, sending the ith variable to the ith generator, I get a surjective map. Nothing mysterious. Now I'm interested in the kernel. If you think, I'm doing exactly what I did earlier with my curve. My curve was this guy, and I told you we must find equations. And these equations, as you have noticed, certainly were binomials. And why were they binomials? Because this guy is actually essentially a semigroup algebra. So the kernel is generated by binomials. Think of it this way. This is a graded map. It's homogeneous. It sends each homogeneous component here to an homogeneous component there. If you have a polynomial in the kernel, you can decompose it as a sum of homogeneous polynomials. Now, a homogeneous polynomial which is in the kernel cannot be a monomial, because monomials don't go to zero under this map. So it has to contain at least two monomials. But because it is homogeneous, the two monomials must go to the same graded component. But there, one is a multiple of the other. So my two monomials, if I take my two monomials which were in the kernel, there must be some lambda such that the difference goes to zero. So you start from a polynomial, you look at its homogeneous component. In each homogeneous component, you take a binomial, and you realize, aha, this binomial has to be in the kernel. So I can remove it from my polynomial, because my polynomial is in the kernel, I remove something in the kernel. And I continue, and finally my polynomial was a sum or a composition of binomials. So the kernel has to be generated by binomials, and what is generated by binomials? Toric varieties. So, so we have to a rational valuation, we have associated a generalized toric variety. I say generalized because usually toric varieties live in finite dimensional spaces, and this one does not in general. But we are guided by that. Why? Because toric varieties we know how to resolve. Very simply, I want to explain that to you. It's very important because the whole idea of my approach is to reduce the problem of local uniformization to the problem of embedded resolution of singularities of affine toric varieties. And the problem of resolution of embedded resolution of singularities of affine toric varieties is solved. It's something I did with my student Pedro González Pérez years ago, and I'm going to explain to you in an example why it is so simple. And I'm not talking about resolution of singularities of toric varieties. If you know toric geometry, first of all, usually you know only about normal toric varieties, and they have a resolution which is not embedded. They just produce a birational map, which is non-singular. But here I'm talking about embedded and non-normal toric varieties. So it's a little bit different, but we are nevertheless going to use the basic theorem which resolves singularities of normal toric varieties.
You say you did this some time ago. How long ago is some time ago? 10 years ago, 30 years ago, 10 years ago?
No, more than that, I think. Yeah, more than 10. Okay. I can tell you later, but 15, something like that. I will, yes. Tomorrow, if people are interested, I can produce a list of references to look at. So let me show you how it works for one binomial. That's the way to understand. So I have this binomial, and I remove the constant because it's not really important. And I want to produce a toric map. So how many of you are unfamiliar with toric geometry? You all know some toric geometry. Wonderful. You too.
Well, I don't know where I should put myself on this. Probably one of the baby ones.
Okay, so I'll assume you know. So how do so my toric variety, which I will call maybe, let me call it X, it lives in some affine space. I'm only talking over my field K. And now I'm going to assume that K is algebraically closed for a good reason, not for simplicity. So this is my toric variety defined by binomials. I want to produce a toric map, Z, from a non-singular toric to an, which resolves the singularities of my toric variety. This is embedded resolution. So the strict transform of X becomes non-singular in Z and transversal to the toric boundary. How do I produce such maps? By finding regular fans with support the first quadrant. Okay, we all agree to that? The affine space corresponds to the first quadrant from the toric viewpoint, to the fan, which consists of the first quadrant and the faces. And then if I want to make a birational toric map, I just refine this fan. And if I want the result to be regular, I refine it by regular fans. Everyone okay? Oh, very good. Now, but I want something to happen here. Now, a regular fan, I write like this. These are vectors which lives in the dual space, according to which everybody calls n, which is unfortunate because it's not the same as this one. Sorry? This is a cone generated by the vectors a1 up to an. So, okay. Let me change this. It's too late, anyway. Now, when I have a fan like that, it gives me a map from a copy of AM to AM. Here I have coordinates y1, ym. Here I have coordinates u1, um. And the map is given like this. ui is y1 to the a1i, ym to the a_n_i. This is an M.
Sorry, again, it's a stupid question, but so this is a cone, this is not a fan. So you're considering the cone.
I'm looking at one cone of the fan at a time. Okay? Because it's only there that I can write down explicitly. And now, now I'm going to say something about my fan. M minus this binomial corresponds to a vector. Oh my God. Don't snicker. In the dual of M. Okay? And this vector corresponds to a certain hyperplane in NR, in the real vector space generated by this lattice. Okay? This is a hyperplane, and because my binomial has to be a true binomial, that means neither m nor n is 0. The components of the vector m minus n have different signs, which means that this hyperplane meets the positive quadrant. Okay, you see the picture? Now, I take a fan sigma with support the positive quadrant. which is compatible with the hyperplane. What does it mean? It means that every cone in my fan intersects the hyperplane along a face, which may be the origin, of course. Okay? Now, this means in particular that if I have a cone like that, sigma is entirely on one side of H. This is a tautology. To say that it's compatible is precisely to say that the hyperplane doesn't cut through sigma. All right, but this means that if I take my vectors, it means that the scalar product AI m minus n either 0 or all of the same sign. So let's say either 0 or positive, or positive. Okay, that's exactly what it means to say that the cone is entirely on one side of the hyperplane. Okay, so now let's look at the transform of this binomial by the map which is here. My binomial becomes y to the a1 m, y1, y m to the a n m m minus y1 to the a1 n, ym to the am n. But look at that. I can rewrite this as y1 to the a1 n dot and to the am n factor y1 to the a1 m minus n, ym to the am m minus n minus 1. Because all these are either 0 or positive. So this is an honest monomial. So I can factor out this guy. Okay? But this hypersurface is non-singular in any characteristic. Because the vector m minus n, because it's the kernel actually of a map, it has to be primitive. It's a primitive vector. Its coordinates have no common divisor. I apply a transformation by vectors which generate a regular cone. That means they are the cone that generate, they are a basis of the integral lattice. So these have to be also co-prime. So these exponents here are co-prime. The vector a1 ai m minus n is primitive. So I'm finished. I have produced a map corresponding to sigma, which is a proper birational map to the affine space, and the strict transform of my binomial hypersurface is non-singular, and also transversal to the toric boundary. If you want to look at the picture, of course, if all the exponents are positive, I have lost, because it means my hypersurface will not touch the exceptional divisor. The exceptional divisor is the vanishing of some of the y's. But if all the exponents are strictly positive, it means my hypersurface will sort of avoid touching the exceptional divisor. So the chart in which I'm interested, where the strict transform of my hypersurface will appear, is the chart where some of the vectors ai will be in the hyperplane. So I'm interested only in the cones. I have my hyperplane, something like that. Okay, it cuts through. And I'm interested only in the cones which have some vectors lying in the hyperplane, because those are where see something. And in fact, the only really interesting ones are those where all the vectors except one are in the hyperplane, because those correspond to the charts where the equation will be simplest. And in fact, in those charts, the equation will be yn minus 1 equals 0. So I can always manage that the strict transform of my hypersurface in every chart which is where it appears has an equation like that. So you cannot make more smooth and more transversal to the toric boundary. Okay? Now, if I have many binomials, I have to use something a little bit deeper. Of course, if my ideal is assuming it's generated by finitely many binomials, I can always find a fan. Oh, I forgot to say that the theorem of resolution of toric variety says that whenever I have a system of rational cones, like a system of rational hyperplanes, like here, I can always find a regular fan which is compatible with all those hyperplanes. I'm using that. That's the theorem of resolution of singularities of fans, if you like, which is used, again, in the resolution of singularities of normal toric varieties. Whenever you have a system of convex rational cones, whatever, in this case, hyperplanes, you can always find regular fans which are compatible with all of them. So if I have many binomials, I have as many hyperplanes, I can find a fan which is fans which are compatible with all those hyperplanes. That means the strict transforms of all the hypersurfaces will be non-singular, but I have no guarantee that their intersections will be transversal. For that, I have to work a little. Okay? So to prove that the intersections are transversal, one uses a formula. So I told you this as something miraculous, because in this case, really, you resolve singularities in such a simple way. So where is my... Well, anyway. Suppose I have finite collections of binomials. Now I have finite collection in finite dimensions. And so this defines a certain... So this ideal defines a certain subvariety X in AM of K. Now I want to compute the Jacobian minors of X, and I assume that X is of dimension D, and I said C equals M minus D, and so I have this situation of Zm goes to Zd, and the kernel is a lattice, and the binomials here, the vectors ml minus nl, generate the lattice. Beware that they do not, in general, generate the lattice minimally, because there is a well-known difficulty that when you want to find the ideal, which is the kernel, you can take only positive combinations of vectors. So if you just take a basis of this lattice, it will not, in general, and take a basis of this lattice, take the vectors and write them in this form, it will not, in general, generate the kernel. One must be aware of that. But we have this, and I'm going to write the... yes. So I claim that if I have, let us say, L is in L, L is 1 up to little l, no, capital L, never mind. Let's put it L, whatever. Okay, and so this is the number of equations, and my number of variables, of course, is 1 to m, the index of the variables. Now I want to compute the minors of these equations with respect to a certain subset of C equations. So I take, say, I1, IC, which is a subset of 1L. Let me call this capital I. And I take a capital K, which is a subset of 1M. Subset of the variables, of C variables. Then the formula is not very difficult to compute at all. It says that UA1 up to UAC multiplied by the Jacobian of the equations UM, ML, NL with respect to the variables K. I write it like that. This is for L in I. So I take these particular equations which I've selected here, differentiate with respect to those particular variables which I have selected there. This gives me a certain minor of rank C, and there is an identity like this. This is the product of U to the ML for L in I, times the determinant corresponding to the same lines and columns, so IK, of the matrix of all the vectors ML minus NL. This is true modulo the ideal P generated by the binomials. Let's call this P. It's a prime ideal. This is a very easy exercise. It tells you one important thing, which is that outside of the coordinate hyperplanes, this is non-zero, this is non-zero, then the vanishing or not of the certain Jacobian determinant is totally decided by this combinatorial object, the determinant of a matrix with integral entries. If you think a little bit, you can look at the same toric variety defined by the same binomials, but over Z. You can take the semigroup algebra of gamma over Z. And this contains, or rather this is contained in the semigroup algebra of the group generated by gamma, which is in this case Z to the D. Okay? But this guy, so in the language of toric geometry, this guy is the torus of this toric variety. It is what happens outside of the coordinate hyperplanes. But this guy is obviously smooth over Z. Okay? This one. Not this one, of course, but this one is smooth over Z. And this is the same thing. This tells you the fact that it is smooth over Z, the C by C minus cannot all vanish for any prime P. It means if I take any prime, the fiber of the torus has to be non-singular. But I have equations for this fiber. Of course, they are rather twisted equations, but still these are equations for the torus, if I look outside of the hyperplane. So the fact that this is smooth over Z tells me that for every P, there must be some determinants here which do not vanish. Okay? Now, these determinants not to vanish is exactly what I need for the transforms of my hypersurface equations to meet transversally. It's the Jacobian Criteria. This is exactly what I need. Okay? So this tells me that for every P, once I have found my fan, for every P, I can find the proper minors, the proper equations. The equations will still be, the street transform will be smooth, and this tells me that they will meet transversally. So I will have a resolution of singularities, an embedded resolution of singularities of my toric variety. Okay? So I think it's surprisingly easy. I have another proof of this, but I don't have the time. I have another proof which I like better, but I don't have the time to explain it.
You gave us the proof you don't like.
Exactly. Because it's fast. Yeah. Okay, so what does this have to do with local uniformization? Well, you look at this, and you look at the thing I told you, that the associated graded ring, it's erased, the associated graded ring is essentially a toric variety. So let's look at the case where the semigroup is finitely generated. And I will show you that this induces local uniformization for all those variations where you can be sure that the semigroup is finitely generated. Why? There is a principle in algebra, not only commutative algebra, there is a principle in algebra which I think should be better known. It's beginning to be better known because there are lots of people doing what is called toric degeneration. But it's still not well known enough. The principle is the following. Whenever you have a ring and a filtration, you have a ring R and a filtration. So in my case, the The filtration is a little bit complicated, but it's the filtration by the P phi of R. So you have a ring, you have a filtration. You have a filtration, you have an associated graded ring. Now, the reasonable question to ask is what information does the associated graded ring contain about the ring? There is a very, very large literature about that from a viewpoint which is rather algebraic in the style, but usually for the M-adic filtration of a local ring. For example, if the graded ring is Gorenstein, the ring is Gorenstein. If it's Cohen-Macaulay, the ring is Cohen-Macaulay. But then the difficult questions are in the other direction. When can I guarantee that the graded ring is something or other from some hypothesis on the ring? Here we are playing a different game. We are doing geometry. And I say, whenever you have that, you have a family. The base may be rather large, as we shall see, but where the general fiber is R, and the special fiber is GRU R. And this has geometry. And the important thing is that this family tends to be, in some sense, equisingular. We are going to see that it's a very exotic type of equisingularity, and at least I don't understand it in general, but I think it's a general principle that this family tends to be equisingular. Let me give you the simplest example. We started with a curve. Okay, let me write it O. Irreducible curve, and I look at it here. I told you there is a semigroup, and the T-adic valuation gives me an associated graded ring. What is the associated graded ring? This you know by now. K is algebraically closed, any characteristic, in fact. It's T to the gamma 1, T to the gamma whatever, C, where the semigroup is generated by gamma 1, gamma C. You agree? We've seen that already, earlier. Now, to look at it a little bit more closely, it means I have elements in O, let us say C1, which can be written as T to the gamma 1 plus higher order. And C2 is T to the gamma 2 plus higher order, and so on, up to Cc. Now, so C1 of T, C2 of T equals this, okay? Now, let me look at, so even if my curve was a plane curve to start with, okay, I have those elements. Because plane curved, the number of generators of the semigroup may be as large as you want. And I have those elements in my curve. Now let me look at V to the minus gamma 1, psi 1 of Vt. V to the gamma minus gamma C, psi C of Vt. What does this look like? Well, it looks like T to the gamma 1 plus V times something. Here is same. T to the gamma C plus V times something, or V to some power, in fact, times something. You agree? So this is a family, but now a family of space curves, okay, which for V non-zero is isomorphic to my original curve, because the ring of my curve is exactly the ring generated by those series inside Kt. So for V non-zero, all I've done is a change of parameter and a change of coordinates. Very innocuous. So for V non-zero, it's isomorphic to my curve. And of course, for V equals 0, it gives me the monomial curve, which corresponds to my semigroup, which is a toric variety, of course. So I've made a family where the general fiber is my original curve, plane or not, who cares? And the special fiber is the graded ring, which is in general not plane, because its embedding dimension is the number of generators of the semigroup. Okay? And this family is equisingular in a very, very nice way. It satisfies the Whitney conditions. It has simultaneous normalization and so on. All that it doesn't have is constant embedding dimension. So the idea that you must keep in mind is that if you want to really understand your curve, you must first re-embed it in a larger space. Once it is in that larger space, you can specialize it to the monomial curve. And if you study that specialization, you learn a lot about your curve. Okay? And this is the program I want to follow in general. You learn a lot. In particular, as I said, the monomial curve is a toric variety. Its equations are binomials. Okay? So I have many toric resolutions of this part, as I just explained. Okay? Now, the whole idea is that some of those toric maps, if I choose them carefully, they will resolve, so to speak, the whole thing. What do I have to do? If I look at the equations, I'm going to stop in a few minutes. What I'm going to show you next time is this. The equations of this guy will be deformations of the binomial equations. So here I've given you a parametric representation because it's faster. But the thing I'm really interested in is to look at the binomials, which are equations for the monomial curve, and show you that this family of curves can be obtained by adding terms to those binomials, but which have higher weight. This is the important the weight being that U1 is given the weight gamma 1, U2 is given the weight gamma 2, and so on. So this is called what I call an overweight deformation. And the thing is that once you are in this situation where you know that you have an overweight deformation, you can prove that some of the toric resolutions of this part will resolve the whole thing. What does that mean? It means that when I look, I resolve my toric variety. I showed you, I have a center after resolution. At that center, think of my y minus 1. At that center, my toric variety is resolved. It's very, very nice. It's just like something. And then what I want is that when I add the perturbation and I take the strict transform, what I get is a deformation of this guy. If I succeed in doing that, I win, because a deformation of something smooth is smooth. So what do I have to prove? That when I make you remember my division, y1 to the a1n, when I factor out the exceptional divisor, I want to be able to factor it out of everything, because then I win. If the strict transform of these equations are deformations of the strict transforms of the binomials, I win, because then I'm deforming something which I know to be smooth. Okay? So, but then it's a completely combinatorial problem. You have to prove certain inequalities, which I will show tomorrow, I think. You have to prove that certain inequalities hold. In this case, and more generally, in the case of valuations of rank 1, which I have not explained yet. And it's very easy. In the general case of higher rank, it's a mess, but it's written down. Okay? So that's the idea of the proof of local uniformization in the case where the semigroup is finitely generated. And I will tell you that the case of finitely generated semigroup corresponds to what is known as Abianca valuations in any characteristic. This was a result which was more or less known, I think, in characteristic 0 by work of Kutkowski, but it's now proved in arbitrary characteristic. And I will stop here.